Right, so we'll start the lecture now. So for those who are online, please keep yourselves on mute. If you have a question, raise your hand. I will ask you to speak up after that. Thank you. So in the last lecture, we had started a discussion on, let's make it full screen. Sorry. Yeah, so we had started a discussion on the modeling. So we had modeled the 1D heat conduction equation, which is an example of an elliptic equation for us. So this is going to help us formulate the methods for solving elliptic equations to start with in this course. So we took a one-dimensional fin, although the fin in reality is three-dimensional, but we said that given the geometric condition and the situation, we can consider that as a fin where the temperature, that's the unknown variable, is varying only as a function of x. Okay, so if we take that, we do some energy conservation or power conservation, energy per unit time, what do we get under the limit that your delta x tends to 0, because this is a governing differential equation. So this is valid continuously on the domain. So this we get a governing differential equation which has a derivative, a second derivative with respect to theta, with respect to x, and we also have a term of theta. Just keep checking if you're still online. Right, and then we have two boundary conditions. One is on the left hand side and one's on the right hand side. So this is simple because it's one dimensional, so we have only left and right boundaries. On the left boundary, we have temperature specified, so that's called a Dirichlet boundary condition, as we've discussed. And the right boundary is it's an insulated fin. So if it's insulated, that means the heat transfer is net rate of heat transfer is 0, and heat transfer is due to conduction just out of the surface. If you think of the solid surface just on the left of the edge, so you will have heat conduction out is 0. So, and the Fourier's law of heat conduction says that the rate of heat conduction is simply minus k times d theta by dx, theta being the temperature. So in that case, we simply get d theta by dx at the right boundary is equal to 0. That's a Neumann boundary condition, or in this case it's homogeneous Neumann, because your d theta by dx is actually 0. If it was non-zero, it would have been simply Neumann. Okay, so that is the set of differential equations that we want. Now we have to discretize that, because in CFD we have to discretize that on a domain where you have some discrete nodes available, so that now you can solve the difference equations and get the information of theta on the specific nodes in the domain. So for that we have to define a node. So we say that let xi be the x position of some node that we have defined. So if you see this figure, we have theta naught, which is the left boundary, and theta n being the temperature at the right boundary, and everything in between, all the discrete thetas are at discrete xi values. So xi goes from x naught all the way to xn, and it will have some value depending on the position where it is. So the second derivative at any xi is discretized using the center difference method that we have already discussed. On the right hand side, we simply have theta. So theta is at theta I. Okay. Everything else is defined. So theta f is temperature of the fluid, beta is some combination of parameters, and so on. So when you combine the unknown terms on the left hand side and the known terms on the right hand side, you get a linear equation, or in this case actually a system of linear equations, because what we are seeing here is that our I in this case, I mean this equation is written for xi. Now my xi will vary, right, for all the interior points. So we will start from this today. So I goes from 1 all the way to n minus 1. So that allows us to cover all the interior points. So this allows us to cover all the interior points, and then we have two boundary points, theta naught and theta n, For that we will be using the boundary conditions. So this when we cover all the interior points, we get n minus 1 equations, and remember we are applying the governing differential equation on the interior points. So we will say from governing differential equation, or that is actually governing difference equation. So this is governing difference equation. So that is the one we are talking about. And then we have two boundary conditions. So boundary condition will give us two equations, and collectively we have a total of n plus 1 equations, for a total of n plus 1 theta i's. So you have n plus 1 theta I values, as you can see from the figure on the top, and you have n plus 1 equations, so that looks tractable. You should be able to solve it. Is that clear? Any questions? So let us see how we will be able to solve this. So let us prepare a matrix form of this system. So the first equation is actually starting from, let us write all the unknowns here. Okay, so we have a total of n plus 1 theta values, temperature values, and then for the first equation is simply, if you look at the boundary condition again, it's theta at x equal to 0 is theta naught tilde. So basically what we have is, we have 1 times theta naught is equal to theta naught tilde. Okay, so that is the first equation. The second equation is then it starts to be the governing differential equation. So governing differential equation, if you look at, it's for the point xi. Okay, this remember governing differential equation was written for xi, right. So that means theta I is the temperature at that xi, and I am using one forward theta and one backward theta to write the expression. So just focus on this one, put a star here, that we are using to write the equation. So the equation is for the second equation that we are writing is for theta 1, because you are applying the differential equation at theta 1. So theta 1, the coefficient of theta 1 is minus 2 upon delta x squared minus beta. So that is we will call it d, that is the coefficient of theta 1, and the coefficient of theta naught is simply 1 by delta x squared, that is this one. So we will call this b, and the coefficient of theta 2 in this case is 1 upon delta x squared as well, but we will call this a, and then everything else is 0. On the right hand side we have minus beta times theta f. You can check it, you can expand it and see that this actually is the differential equation, the governing difference equation for the point theta 1, or for the written at the point x1. And similarly, I do not need to check every equation now, I can see the pattern. And so on. So this you can see I have used the word D, letter D here, because that stands for the diagonal in the matrix. So let us define D. Is that clear? And we keep doing that until we reach the right boundary point. Now, for the right boundary point, the equation is, let's go up again. Did we discretize that? We did not. So, the right boundary is d theta by dx at x equal to L is equal to 0. So, we need to discretize that as well, because that is a derivative now, it is not a Dirichlet condition. So, how can we discretize d theta by dx at the right boundary? Can I use center difference method here? Exactly, I cannot use center difference because there is no right point here. There is only a point theta n or xn. So, I can use backward difference here. Right. So, if I use backward difference to discretize the right boundary condition, let us do it here. So, that will be theta at the boundary minus theta at a left point upon the interval size is equal to 0. So, that simply turns out to be minus 1 times theta n minus 1 plus 1 times theta n is equal to 0. Right. So, in the matrix form, what happens is, since we have that equation is for theta n, so the diagonal term is 1 and the one before the diagonal is minus 1, and then everything else is 0. So, let us look at the sizes. So, the size of the vector theta is of size n plus 1. The right hand side R vector is also n plus 1, and the size of the matrix A is, it is a square matrix of size n plus 1 cross n plus 1. So, I think it seems that we have written the matrix form of the linear system correctly. I am sure if I give you the values of theta naught tilde, beta, theta f, for calculating the diagonal you need delta x value, and for calculating a and b you also need delta x value. If I give you all these values, you should be able to plug in the numbers and just solve the system. There are different ways to solve it. The easiest way to think about it is to simply calculate the inverse, multiply by the inverse of a on both sides. So, that gives you the theta vector as the A inverse of matrix A times the vector R, right. That should be easy. Everybody has done a course in linear algebra here, so you should be able to understand that. So, let us write some notes. So, as I said, we can solve the linear system A theta equals R by calculating the inverse of A and then multiplying both sides on the left hand side by A inverse. but that will be inefficient. Can anyone think of why it would be inefficient to calculate the inverse of A in this particular condition? Please raise your hand if you have the answer. The magnitude of A inverse, determinant of A inverse, then it's not defined. If it's not defined, then you don't have a solution. Okay, so you know the condition under which this is not. If there's no unique solution, then A inverse or A would become singular. But we don't want that. I mean, if there's no solution, then our problem is not well posed. Okay, so that will not happen if everything is well posed. Think in terms of computer memory storage. Now let n be, let's say 10,000. That's a valid number, right? Typically you'll want 10,000 points if you are calculating the temperature at different points. So n plus 1 times n plus 1, that's 10 to the power of 6, 1 million, right? So if you need a couple of bytes to store a number, typically let's say you need 4 bytes or 8 bytes to store a number, then you have 8 times 1 million, that 8 megabyte, right? So that's the amount of bytes you need to store the matrix A. Now 1000 is a small number. If you actually go to 3 dimensions, you have n by n matrix, you will see later. So that will be, because the number of unknowns will be much larger in that case. So what happens is, actually the matrix will be much larger in size. So what happens is, if your number of unknowns are n in all 3 directions, then the total number of unknowns are n cubed. So the size of theta is n cubed. So the size of A has to be n cubed times n cubed if you are writing a matrix system like this, right? Because you will have an equation for each point. You have n cubed number of points. N was 1000, so you have 10 to the power of 9 points. So you have 10 to the 9 times 10 to the 9 is the size of the square of that. So you're talking about 10 to the 18. So things actually quite quickly go out of hand if you're talking about realistic numbers in terms of sizes of the matrices that you're dealing with. And these matrices have to be stored in the memory of the computer, in the RAM. And RAM is expensive, you know that, as compared to storage in the hard drive. Okay, but do we really need to store all the numbers here in the matrix? Mostly it is 0, right? Except for the diagonal, above diagonal and below diagonal. So you have 3 bands, that's it. So the size of the diagonal is n plus 1. So you have n plus 1 times 3. Rather than square of n plus 1, you have only 3 times n plus 1. So all we need to do is, in the matrix A, we need to store only 3 times n plus 1. So in this course, it's not just about algorithms, it's also about how to implement them. So we'll keep thinking in all directions. So we'll say that matrix A is tridiagonal. Or another way to say is the linear system is a tridiagonal system. Right. I saw the message. So if you are storing only once, even then you have to store it. Okay. So if you have to store zeros, it is actually not useful. So we'll avoid storing zeros and lots of zeros, because that's just wasting memory. Right. So what are we storing? We are storing 4 one-dimensional arrays So one's below diagonal, one's diagonal, one is above diagonal, one's right hand side. Even the right hand side has to be stored. Now in this condition, in this situation, you might argue that even above and below diagonal terms are all the same. It's 1 by delta x squared. But let's keep it a bit general in the sense that delta x could be non-homogeneous. So if delta x is non-homogeneous, then delta x could be different for different intervals. So then you have to store the delta x value for each interval. Even let's say there is no pattern to the, there is no structure to the way delta x varies from one element to the other element. So then we have to store the value. Okay. So in that sense, we will develop the algorithm so that we are storing all the values of diagonals below and above diagonal values. Although we could have simply stored one number and then use that everywhere, but we will store all of them to keep the algorithm general for our case. Right. So even if I store these, when I calculate the A inverse, do you think the inverse of A would be tridiagonal as well? Not necessarily. In fact, it is not the case. So when you calculate the inverse of a tridiagonal system, you get a system which is actually quite dense. So I want to avoid calculating the inverse of A to solving the linear system. Are we aware of any methods which can be used to solve this linear system without calculating the inverse of A? Gaussian elimination. Right. We all know that. That's the first method we learn in solving linear equations. You take a pivot, you solve, you make the diagonal, you make the below diagonal elements 0. So you get an upper triangular matrix in the modified system, and then each operation that you do to modify the system is basically modifying equation by adding equations to each other in some combination. Right. So I will not discuss Gaussian elimination, that everybody is aware of. If not, then you can recapitulate that in your linear algebra course. So we will use that. So Gaussian elimination has two steps. One is called forward elimination. And then you have backward substitution. Right, the forward elimination is where you convert it to an upper triangular matrix, and backward substitution is where you start evaluating the value of thetas going from the last equation to the first equation. So if you had a modified system where you have all these lower diagonal terms 0 and the above diagonals are there, and then you have the matrix vector theta, and then you have some modified right hand side. So you can see that the last equation has only one term. So you have that coefficient d times theta n is equal to r n. So you can calculate theta n. So once you have theta n, the second last equation has two terms, one for theta n, one for theta n minus 1, but theta n is already known now. So you can use that, you can get theta n minus 1, and you keep doing that. So it's called backward substitution. So there are two steps in the algorithm here. In fact, the Gaussian elimination becomes much simpler because you only have 3 bands. Otherwise, you have to make if you start with one pivot here, then you have to make all the terms below that pivot to be 0. But here what we have is, if you see the linear system, let us say your pivot was, let us start with this one. This was your pivot. Then below this equation, all you have is only b as a non-zero term. Everything else is 0. Right? So you need to only do one step in the algorithm when you identify a pivot. So it's still Gaussian elimination, except that it's much simplified. You don't have to make all the equations below that 0. Only one equation will have a non-zero term below the pivot. So we'll discuss the algorithm, but I'll suggest you go home and recap that as well. Theta sum calculate, we are calculating it. So yes, you have to store it. So you have n plus 1 unknowns there as well. So that you will store. Yes, yes, you're right. I mean, we have we calculate. Good point. So we have to use that space as well. So this Gaussian elimination for a tridiagonal system is simplified, as we just discussed, and this is actually called a tridiagonal matrix algorithm, TDMA. So if you see the word TDMA written, don't get intimidated. It's simply Gaussian elimination applied to the tridiagonal system. So I'll just write a homework here, revise right. So now let's look at the algorithm. Now I'll write the system in such a way that the left boundary, that's theta naught, because see left is Dirichlet conditions, I am not actually solving for anything there. So if you look at the linear system again that we have just written, the first equation is actually trivial. It says theta naught is equal to theta naught tilde. So that's a known value, we are not solving for it. So let's not include that, and then we'll have the linear system starting from there. So now we will be discussing the tridiagonal matrix algorithm. So we start with the diagonal term, then we have above diagonal, and then we have all zeros. So this time we are starting from theta 1 because theta naught is already known. Now if I write the equation for theta 1 again, so it was 1 upon delta x squared times theta naught, because the left point. Now theta naught is already known.
जो आपने पहले कैलकुलेट करवाया था उसमें थीटा 1 के लिए पीडीए से शुरू हुआ।
Wait for a few seconds, you will see why. So this is our first equation. Now in this equation we are solving for theta 1. So that's the diagonal. So this coefficient should be the diagonal coefficient, but this is already known. Everything that is known goes to right hand side. So what I'll do is I will remove this from here and I'll put it here. Now it's clear? Is that clear? Okay. So to discuss the algorithm, what I'll do is I'll simply use R on the right hand side, and you know what R is as I've just written above. So the coefficients for matrix A, we'll start with, so the subscript will be used for the row number, because that's how we'll be storing them in the arrays. So the first diagonal here is D1, then we have A1, and then we have all zeros. In the second row, we start with B2, then we have D2, then we have A2, and then all zeros all the way. And then in the last equation, or the second last equation, we'll have diagonal n minus 1. To the right of it, we'll have a n minus 1, and to the left of it, we'll have b n minus 1. And the final equation has 1 minus 1 and all zeros. Sorry? Yes, you're right. Yeah. Thanks for the correction. Right. So this one, that's the bottom right term in the matrix A, is actually dn, and the minus 1 is bn. So that's how we'll be storing them. So I'll be using these indices now in writing the algorithm. Any questions till this point?
It will be same as A1, A2, A3.
For this, for the present discussion, yes. But while writing the algorithm, we will keep them different. Because see, A1, A2, A3, what are they? They are 1 by delta x squared. Now, if delta x is varying from interval to interval, then they may be different. Now, there are situations where you do not even know how they will vary until you solve the problem. So, it's called adaptive meshing or adaptive gridding, where the grid size adapts with the solution. Now, that's a bit complicated, we will not discuss it as a part of this course, but you will see that feature in the software, in the codes. So, there what it means is that you don't even know how delta x will change unless you start solving the problem. Okay, so, we will have to store them all differently, separately. Right, so let's now start discussing the algorithm. So, the first equation, sorry, so let's write the algorithm. We need the linear system for it. So, the first pivot we have is D1. So, for that pivot, what you do is you make the row, all the terms in equations below that pivot 0. That's how you reach the upper triangular form. So, in this case, we only have one equation, which is row number 2, that has a non-zero term below D1. So, that is B1. So, the row operation we do is on R2 we do R2 minus R1 times B2 upon D1. So, you can see that if I do this row operation on row number 2, what happens is the term B2 becomes 0, and that is what the aim is. But in the process, other terms will also change. So, I can say B2 becomes 0, but D2 will get modified now. So, what is the new D2 value? It's the same operation. Okay. So, the term above D2 was A1. So, A1 gets multiplied by B2 upon D1, and then you subtract that term from D2. What happens to A2? A2 remains the same because the term above was 0. So, you multiply anything to 0 and subtract that from A2, you get A2 only. Does the right hand side also change? Are we all happy with this? So let's write the algorithm for this. Now in this case, now this was pivot D1, but you can think of an arbitrary pivot now. And we'll do this a lot in this course. I mean, this course is all about computing, so we should have the algorithm that we should be able to then implement in our programming language. So I goes from 2 to n, because remember that we are modifying. So this was step number 1 where we modified row number 2. In the next step, we will start with the new pivot, which is D2, right? A modified D2 now, but still D2. And that also tells us why we were storing all the D values, even though they are all the same, because they will start getting modified very soon. So the D2 has gotten modified. Now with this modified D2 as a pivot, I will make a change in row number 3 now, right? So we start with change in row number 2. That's the reason index I starts from 2, and then it goes to all the way to a change in row number n. So the first thing we do is see the B2, B3 and so on, they'll all become 0. That is the whole aim. So there is no need to store any information about that. B's will become 0 ultimately. So let's look at this equation, the starred equation, to write this step in the algorithm. Can we, in the class sitting, people sitting here, can you see the terms that I am writing on the right hand side, bottom? Okay. So this was forward elimination step. That's pretty much it. Next part is backward substitution. So in backward substitution, it's much more straightforward. The first thing you do is you calculate theta n as Rn divided by dn, right? Because now you have an upper triangular matrix, so all you have is a diagonal in the last row. There is no below diagonal term because it's an upper triangular matrix. So once you have the theta at the last, then you start using that to substituting that in the rows previous to it and so on. So then it simply becomes we get a loop here as well. Now this time we start from n minus 1 because that is the second last row that we are visiting, and we go all the way to the first row because the first row is the equation for theta 1. So in the second last row, which is row n minus 1, you will have, you basically are solving for theta n minus 1. So, you have a diagonal term which is dn minus 1, and you have an above diagonal term which is an minus 1, and you have a corresponding rn minus 1. So, when we write the equation, we have dn minus 1 times theta n minus 1 plus an minus 1 times theta n is equal to r n minus 1. Yes. No, actually it has become much simpler. Earlier we had 3 bands, a diagonal, a below diagonal, and above diagonal. When now after doing all the forward elimination steps, it's become upper triangular. So there's only 2 bands now, diagonal and above diagonal. We are not storing it. Where did we store it? See the algorithm. We are using d of I, a of I, r of I. So these are all vectors. These are all arrays. I am showing that to you by drawing the matrix, but that does not mean I am storing all the zeros. If here in the algorithm I had a of I comma j, that would mean that I am storing all the elements. But you can see in the algorithm we only have arrays. Right, so we are solving solving this for theta n minus 1. I am just writing this equation for a template. So this becomes r of I, because it's row n minus 1 here. So I is n minus 1 minus a of I times theta of I plus 1 whole divided by d of I. Okay, so you can check it also works for all r values for value of I less than n minus 1. So I wrote n minus 1 equation for just the template, but it works for any I value. But remember, you have to go in this order. You cannot go in any order. You have to start from calculating theta n, then start going backwards. Otherwise, it won't work. Any questions? It is there in the forward elimination step. You check the algorithm yourself, go home and try to write the Gaussian elimination yourself and see that in backward substitution B will not come. B will not come because it's upper triangular now. We have made all the B's 0. That was the whole process of Gaussian elimination. Why would B even appear in backward substitution? Right, so we are done with today's lecture. Any questions? Okay. So typically what happens is, you will see that now everybody who has done a fluid mechanics course or an equivalent course will know the idea of non-dimensionalization. Right. You have learned about the Buckingham pi theorem? Yes? So rather than working with dimensional quantities, we tend to work with non-dimensional quantities, because that process of working with non-dimensional quantities reduces the parameter space. So if you have a certain number of parameters, with non-dimensional equations, you reduce the parameters typically by 3. That depends on the number of fundamental dimensions you have in the equation. But the process of non-dimensionalization will make things much more easier for us to handle. So in the lecture that we have, or in the lab, that we will see, you will see that the lab is already uploaded. Labs 1 and 2 are already there on Moodle. You can have a look at it, at the problems. So we will see that we are solving the non-dimensional form of the equation. So what I will do is I will share the slides or the notes for non-dimensionalization. to avoid wasting time in the class, but do understand that because those are the equation. We will solve the non-dimensional form of the equation in the lab rather than solving the dimensional forms. So, you might see that x is varying not from 0 to L, but it is varying from 0 to 1 because we have non-dimensionalized that by the length of the domain. So, that makes things much easier for us as well to handle. Okay. Right. So, now we will meet on Saturday as we discussed for the lab. Although I wanted to have the lab session today, but because of this road closures and all, we thought we will have a lab when everybody is there. So, what I will do is I will float a short poll on Google Spaces. Is there anyone who has not joined Google Spaces? Yes. So, please join Google Spaces. You go to Moodle in the announcement sections.